Jai Hind students, welcome to my YouTube channel. Students, you don't always get what you wish for. Actually, you get what you work for. It's not about how badly you want it. Actually, it's about how hard you are willing to work for it. So students, with that note, let's begin this session. Today we are supposed to discuss some numericals which are based on the topics which we have discussed in the previous 2-3 lectures. It's actually about the magnetic force, the torque experienced applying Fleming's left-hand rule, right? So let's start with the first question then. Students, we will begin with question number 5, right? Let's start with question number 5. This is the question given. I will explain it. It is a vertical plane in which a circular current carrying loop is given, and this circular current carrying loop is of radius r, and I1 is the current which is flowing through it in the anti-clockwise direction. And this dotted line, it's the axis. Axis means any imaginary line which is passing through the center of the loop and perpendicular to its plane. So this is another conductor B which is in the form of a rod, and here current I2 is flowing along this direction, right? What we are supposed to find is, we are supposed to find out the expression for the magnetic force exerted by A on B and B on A. So that is our objective. So again I repeat students, this is a circular current carrying coil, this is conductor A, and conductor B is in the form of straight rod, that is conductor B, right? Both are lying in this manner. The conductor B, which is in the form of rod, is lying on the axis of the current carrying coil which acts as conductor A. We are supposed to find out the force exerted by them on each other. That's our objective, right? Before we start solving this question, two concepts must be very clear in your mind. First and foremost, students, always remember, magnetic force between two conductors, between two current carrying conductors, they form action-reaction pair. This we have proved, isn't it? So what I mean to say is that the force exerted by body A on body B would be exactly equal to the force exerted by body B on body A. So the answer of both the parts must be same. So the force exerted by body A on body B, it should be equal to the force exerted by body B on body A. Actually in the vector form, they form action-reaction pair. So in the vector form, it must be represented like this. Equal sign, it represents that both should be of equal magnitude. Negative sign indicates that they are acting on the opposite direction. So they form action-reaction pair, isn't it? Second very important point, students. We are aware any current carrying coil, it acts as a magnetic dipole. If from the face of the loop the current appears to be flowing in the anti-clockwise direction, then that face acts as the north pole, right? So here in the current carrying loop, the current is flowing in the anti-clockwise. So the face of this loop will behave as north, right? So due to this current carrying loop, the magnetic field in this region would be along this direction, along the axis. This is the magnetic field due to conductor A. Again I repeat, students, this is a current carrying coil, isn't it? At the center, or the magnetic field due to that current carrying coil would be along the axis, either along this direction or this direction, but it will be along the axis and perpendicular to its plane. In case the current appears to be flowing in the anti-clockwise direction, this face will act as the north pole, so magnetic field will be away, right? So outside the body of the magnet we are aware, magnetic field lines are directed from north to south, and inside it is from south to north, isn't it? It's in the form of continuous closed loops. So magnetic field in the region where conductor B is located, it will be aligned along the length of the conductor B, right? Now conductor B under the influence of under the influence of magnetic field BA due to conductor 1 will experience a force, will experience a magnetic force which is given by F2 vector is equal to cross product of current element and the magnetic field, isn't it? So current element, it will be I2, the length, suppose it is L, length of the straight conductor, cross the magnetic field which is BA vector. Now look students, this is the cross product. So in magnitude it will be given by I2L BA sine, what's the angle between these two? This is the current element of the straight conductor, and BA vector, it is also directed along the axis. So what's the angle between these two? It's 0 degree. Sine 0 is 0, therefore F2 will be equal to 0. So no force is exerted by body A on body B, and similarly no force will be exerted by body B on body A. Therefore these two conductors won't exert any force on each other. So that's the solution, students. So we are over with question number 5, right? So let's proceed to the next question. Now let's start with the first one. This is a very, very interesting question which is based on the resolution of vector and forming equations. I'll read the question for you. Question number 1 states that a straight conducting rod placed horizontally on an inclined plane of angle 30 degree is prevented from rolling down by applying a magnetic field of 10 Tesla vertically upwards. If the plane is smooth, it means that force of friction is to be neglected. And mass per unit length of the rod is 0.3 kg per meter. Then we are supposed to determine the direction and the magnitude of the current needed to be passed through the rod so as to make the rod stationary, so as to prevent the rod from coming down, right? So this is the situation basically. This is the inclined plane, and the angle which the inclined plane makes to be horizontal, it's given to be 30 degree. Suppose the rod is placed like this. So this is it. This is the rod. Suppose this closer end, it's end A, and the farther end is B. Suppose this is end A, right? So we are supposed to find out the direction of the current which needs to be passed through this rod, and we need to find out the magnitude of that current as well. And as per the question, magnetic field is given to be directed in the vertically upward direction like this. Its strength is given. Anyway, for further clarity, I'll draw this three-dimensional diagram as well, right? This is the inclined plane, suppose, and the rod is placed like this on the inclined plane. It's like this. This is considered to be end A and this is end B. Clear? This is the rod. And this angle is 30 degree. So it's like this. So end A will be only seen by us in this particular diagram. Right? Now what to do is, students, let's draw the forces in the form of vector, all those forces which are acting on this particular body. Right? So one is its weight. Weight, as you are aware, it always acts in the vertically downward direction along the radius towards the center of the earth. This is the weight m into g. The other is the reaction, which always acts perpendicular to the surface on which the body is placed. So in this case, reaction would be perpendicular to the inclined plane, like this. This is the reaction. Now, mg can be resolved into two components, right? So let us resolve mg into two components. This component, we are aware this is 30 degree, this will also be 30 degree, you can easily prove it geometrically. So resolving mg, this component would be mg cos 30, while this component along the inclined plane in the downward direction, it will be mg sin 30, right? Force of friction is absent, right? So this mg sin theta component obviously will make the rod to come down the inclined plane, while this reaction will balance mg cos theta, right? But now our objective is what current needs to be made to pass through this rod so that it experiences a magnetic force which can balance this mg sine 30 so that the rod remains stationary, so that the magnetic force prevents the rod from coming down the inclined plane. So that's our objective, right? So students, let's first find out the direction of the current from A to B or from B to A. Let's consider our current is flowing along this direction from B to A, right? So let's apply this rule, FBI, right? This is magnetic field in the vertically upward direction. FBI, this is the magnetic field which is in the vertically upward direction, right? This is, if suppose current flows in the rod from B to A, then the magnetic force would be acting on the rod towards left. So this magnetic force, if it acts along left, then it will aid the rod in coming down the inclined plane. So in that case, if the current flows from B to A, then in that case like this, FBI, this is B, this is current and this is it. So if the current flows from B to A, then the magnetic force would act towards left and it will aid the rod, it will help the rod in coming down the inclined plane, right? So that won't serve our purpose. So as a result, we can safely conclude that the current in the rod should flow in the opposite direction, that is from A to B. So the current through the rod should be made to flow from A to B, that is along this direction, A to B, in the inward direction. Now let's see, let's apply this rule, FBI. Now this forefinger represents the direction of the magnetic field, like this, it's in the vertically upward direction. This is the direction of the current, isn't it? So it is from A to B, inwards, like this, A to B. Now look students, thumb is pointing towards right. So the magnetic force, in case the current through the rod flows from A to B, would be along this direction, towards right. This is F. This is the magnetic force. Now students, F can also be resolved. This is 30, so this would be also 30 degree. This is corresponding angles, isn't it? So F can be resolved. So it will be F cos 30 and this component would be F sin 30. Now students, the condition that the rod remains stationary is that it should be under the influence of balanced forces. So therefore this reaction, it should get balanced by the sum of these two forces. It should be equal to F sin 30 degree plus mg cos 30 degree, right? These are balanced forces. While on the other hand, F cos 30 degree would be equal to mg sin 30 degree. So when these are the conditions which are satisfied, then only we can prevent the rod from coming down the inclined plane. Clear students? Okay, what is F? F, you are aware students, it's given by IL vector cross B vector. Now rod is placed horizontally, magnetic field is in the vertically upward direction, so the angle between them is 90 degree. Therefore, the magnitude of the magnetic force would be ILB, sin 90 is 1. So F is equal to BIL cos 30. It is equal to mg sin 30. We are supposed to get the value of I, current, right? So current, it will be equal to m by L. This will be the mass per unit length, right? G sin 30 by cos 30, that will give us tan 30 divided by strength of the magnetic field, that is B. Right? So this is the expression. Now we can simply substitute the value and get the answer. So the current would be mass per unit length. It's given to be 0.3 kg per meter. So it is 0.3. Small g, let us consider it to be 10 meter per second square, right? Tan 30. Tan 30 is 1 by root 3. 1 by root 3. And strength of the magnetic field, it is given to be 10 Tesla. So it is 10 Tesla. 10 can get cancelled. So what we get is I is equal to 3 by 10 root 3. So if we rationalize it, what we get? 3 root 3 divided by 10 into 3. So that will give us root 3 by 10, which is 1.732 divided by 10, which in turn will give us 0.1732 ampere. So students, for the rod to remain stationary on the inclined plane, a current of 0.1732 ampere is to be passed through the rod and in the direction from A to B, right? So that's the complete solution. So this was a very, very interesting and important question, and there are various concepts which we have used in solving this question, right? Okay students, we are done with question number 1 then. So let's move on to the next question then. Question number 2. Just watch that figure which is given alongside this question. In which direction will conductor 2 move? Set of 3 conductors are given, right? So let's start with question number 2. Okay, these are the 3 conductors given, 1, 2, 3. Let me draw it over here. This is conductor 1, this is conductor 2, this is conductor 3. All are, the separation between these two is given to be same, that is R, right? And in each of the 3 conductors, the magnitude of the current flowing is given to be same. This is I, and here the current is flowing in the opposite direction. All are straight, parallel, infinitely long current carrying conductors, right? We are supposed to find out the direction, only direction, with which the conductor 2 moves. It will experience a net force towards right, or conductor 2 will experience a net force towards left. That is to be found. It's a common sense question. So in this question, we will make use of the concept that whenever students, we consider 2 parallel straight conductors carrying current in the same direction, then there exists an attractive magnetic force between them. And in case the current in the parallel conductors are flowing in the opposite direction, then the nature of the magnetic force existing between them is repulsive. So we have to make use of this concept in solving this question, right? It's very simple. So let's consider 1 and 2. Let's consider 1 and 2, first 2 conductors. Now look, we are supposed to find out the net force on conductor 2, right? So in the first 2 conductors, 1 and 2, the current are flowing in the same direction. So the nature of the force between them must be attractive. So it will be like this. It will be attractive like this. This is the force. F12 and this is F21. Right? Now consider 2, 3. Because our objective is to find out the net force on conductor 2. So now consider 2, 3. In case of 2, 3, both are parallel current carrying conductors, but currents are flowing in the opposite direction. So they will tend to exert a repulsive force upon each other. So due to these 2, it will experience a force along this direction and it will experience the same force in the other direction. So this is F23 and this is F32. Right students? We are aware magnetic force, it forms action-reaction pair, isn't it? So now concentrate on conductor 2. Concentrate on conductor 2. So what is the net force acting on conductor 2? F23, F21. Both acting in the same direction. So obviously net force will get added up. So net force experienced by conductor 2 would be, so net force experienced by conductor 2 would be F21 plus F23. Isn't it? In which direction? Towards conductor 1. Towards conductor 1. So that will be the answer, students. So, okay students, let's concentrate on question number 3 then. A wire of length 44 centimeter is given. This is a wire of length 44 centimeter. It's given. It is to be converted into a closed loop, right? and is to be placed under the influence of magnetic field of 10 Tesla. If the current of 5 ampere is made to pass through the loop, then for what shape and orientation the loop experiences maximum torque, and we are supposed to find out the magnitude of the maximum torque as well, right? So it's a very, very good question, students. So first and foremost, a basic fact is to be used. That is, torque, first and foremost, the formula is, in vector form it is given by m vector cross b vector. So in magnitude it is given by mb sine theta, right? Theta, as you are aware, it's the angle between the magnetic moment and the magnetic field. Magnetic moment of a current carrying loop is always perpendicular to the plane of the loop. So it is along the normal to the plane of the loop. So magnetic moment is always directed along the normal to the plane of the loop. Therefore, theta, students, it is the angle which the magnetic field makes with the normal to the plane of the loop, right? Now from here it's pretty clear. Tau, it can be represented as NIA B sine theta. Ni is the ampere terms, A is the area of the loop under consideration. Magnetic moment of any current carrying loop is given by product of ampere turns and the area of the loop, isn't it? Now over here, tau would be maximum only when theta is 90 degree, no doubt regarding this. And also, students, area of the loop is to be maximum. So wire is to be converted into such a loop so as to have maximum area. Therefore, tau max, it should be equal to N I A max into B. Sin 90 will obviously become 1. Clear? This is the formula to be used. Now, how to make the area maximum? Here we will make use of a very, very basic mathematical fact, which is, for a given perimeter, the area enclosed by a circle is maximum. So it's a crucial point, it's an important point. So for a given perimeter means for a given length. Given perimeter means given length. This length of the wire is given. So for a given perimeter, the area enclosed by a circle is maximum. So area of a circle would be maximum. So in place of A max, pi r square is to be considered, right? So clear, students? So what should be the shape of that loop under consideration? In order so that it experiences maximum torque, it must attain circular shape. So the loop under consideration must be of circular shape so that its area is maximum. For a given perimeter, the area enclosed by a circle is maximum, right? So let's find out the radius now. This is the length of the wire given, and if it is to be converted into a circular loop, then circumference would be 2 pi r. So by using this, we can easily find out the radius. Pi is 22 by 7 into r. So what to do is 44 get cancelled. So r would be equal to 7 centimeter. So in SI it would be 7 into 10 raised to power minus 2 meter. Right, friends? Okay. Now let's substitute this value over here. Let's find out the magnitude of the maximum torque. N, for a single turn, N would be equal to 1. Current, it's given to be 5. Area of a circular loop, it's pi r square. Pi is again 22 by 7. R square, the square of r square, it would be equal to 49 into 10 raised to power minus 4. Clear, students? And magnetic field, its strength is given to be 10 Tesla. So we can easily solve it, right? So what do you get? It will be 110 multiplied by 7 would be left into 10 raised to power minus 3. So it will be 770 into 10 raised to power minus 3, which is 0.77 Newton meter. So students, this is the magnitude of the maximum torque which this circular current carrying loop will experience. Right? So, maximum torque, we have done it. Shape, we have discussed. Now, orientation. For this, angle theta should be 90 degree. Theta, I have told you students, it is the angle which the normal to the plane of the loop must make with the direction of the magnetic field. So, suppose this is the circular loop under consideration. Right? So, what is the normal? Normal would be like this. This is the normal. Normal means perpendicular to the plane. Suppose this is the plane. So, this is 90 degree. This is theta. So, theta is the angle which the direction of the magnetic field makes with the normal. This is the normal. Normal means perpendicular to the plane of the loop. And magnetic moment is directed along the normal of the loop. So, what's the angle between M and B? It should be 90 degree. So, for that, magnetic field must be along the plane of the loop. So that it makes an angle of 90 degree with the normal to the plane of the loop or with the magnetic moment of the current carrying loop. It is only then that theta would become 90 degree and tau would become maximum. Right, students? So, I'll repeat the answer of the three parts. What shape? It must be circular shape, because for a given perimeter, the area enclosed by a circle is maximum. What orientation? Theta must be 90 degree, which theoretically means that magnetic field must be along the plane of the loop. That is, it must make an angle of 90 degree with the normal to the plane of the loop or with the direction of the magnetic moment of the current carrying loop. Right? And what is the magnitude of the maximum torque? This we have found to be 0.77 Newton meter. And direction of torque, it's along the axis of rotation of the coil. Being an axial vector, torque would be always along the direction of axis of rotation of the coil. Right? So students, we are over with question number 3. Let's proceed with question number 4 then. Fourth question. A cable wire of mass per unit length 0.8 kg per meter is carrying current of 10 ampere along the south to north direction. Okay. Calculate the direction and the magnitude of the magnetic field under the influence of which the cable wire can remain suspended in the air. Now look, because of the weight of a body due to gravity, it will obviously come downwards due to the Earth's attraction, isn't it? Now, we want the cable wire to remain suspended in air. For that, we are aware its weight will act in the downward direction. So, if I want the cable wire to remain suspended in wire, then its weight needs to be balanced by some upward force, isn't it? So here the magnetic force must act in the vertically upward direction. So let's consider on this question then. Let's draw the relevant diagram first. This is suppose north, this is south, this is west, this is east, and this is suppose the vertical. Now as per the question, cable wire is carrying current of 10 ampere along south-north direction. It's given. So this is suppose the cable wire. I am trying to represent it diagrammatically, right? This is the cable wire and direction of the current is from south to north, like this. This is the direction of the current. Suppose this is north, this is south, this is west and this is east, right? So current is flowing from south to north, like this, south to north. Inwards, in this case inwards. If it is considered to be north, south, west, east, then current is flowing in the inward direction. Okay, what about the weight? Weight of this cable wire will act in the vertically downward direction, which is mg. And as I have told you students, in order that the cable wire remains suspended in air, its weight must be balanced by some equal and opposite force, isn't it? So, the force, magnetic force, must act in the vertically upward direction. This must be the direction of the magnetic force. It is in the horizontal plane, a magnetic force must act in the vertically upward direction. So angle within them is 90 degree. We are supposed to find out the direction and the strength of the magnetic field. So students, whenever we consider current carrying conductor under the influence of magnetic field, then it experiences a magnetic force, the direction of which can be given by Fleming's left hand rule in case they are perpendicular to each other, isn't it? So here, do you remember FBI, Federal Bureau of Investigation, isn't it? Thumb represents the force, forefinger represents the magnetic field, central finger represents the direction of the current flowing through the conductor. So these three are mutually perpendicular, right? Out of these three, if the direction of two are known, then the direction of the third one can be easily sorted out, or it can be easily found by using this rule, right? Here FBI, here force is known, the direction of force is known, the direction of the current is known, that is from south to north. So let's apply this rule. F, force, it should be acting in the upward direction, thumb indicating the direction of force. Magnetic field, and this is current. Current should be in the inward direction, not in the outward direction, should be in the inward direction. So what I do is like this. This is F, thumb indicating the force, central finger indicating the current, that is from south to north, inward, south to north. So magnetic field, students, it must be acting towards west, Understood now? Just we need to apply Fleming's left hand rule. Do lot of practice. So, magnetic force must be acting towards west. So, the direction of the magnetic field is, or rather it should be very, very clear, right? All are mutually perpendicular to each other. Now, let's find out the strength of the magnetic field which needs to be applied, right? So, as I've told you, for the cable wire to remain suspended, this magnetic force must be equal and opposite to the weight of the cable wire. Now magnetic force, as you are aware, is given by IL vector cross B vector is equal to mg. What's the angle between the magnetic field and the current carrying element? The rod is in the direction of cable wire is in the direction south to north, and magnetic field is along west. Angle between them is 90 degrees. So ILB sin 90 would be 1 is equal to mg. So strength of the magnetic field, it would be m by L, this will be the mass per unit length, g divided by I. Clear? Okay, so let's substitute the value. Mass per unit length, students, it's given to be 0.8. Small g can be considered to be 10 meter per second square, just for simplicity in calculations, right? And current, it is given to be 10 ampere. So 10 get cancelled. So the magnetic field would be 0.8 Tesla, and in which direction? Towards west. So that's the complete solution, right? Here students, I must remind you, in case you find any difficulty in understanding the concepts while solving these numericals, please go back and watch my earlier videos where theoretically I explained each and every concept in detail. And one more thing students, in my playlist section, I have arranged all my lecture videos chapter wise and class wise. So it won't be any problem in searching a relevant video and watch it. Understood? So please, while watching the lecture videos, watch it in sequence. First theoretical portion should be clear, and only then you will equip yourself. After equipping yourself with all the theoretical knowledge, you will proceed and you will definitely be able to solve numericals that much more with that much more confidence. Right? So with that students, let's end this particular session. In the next lecture, we are going to discuss a very, very important topic of moving coil galvanometer. It's indeed a very important topic, both from CBSE examination point of view as well as from comparative examination point of view, right? So that's actually the last topic in magnetic effects of current, right? So do join me in my next lecture to discuss that very, very important topic, moving coil galvanometer, right? Till then, do take very good care of yourself, and thank you for watching my video.